In this episode of Idea City.
This cloud here that I'm pointing to on the left, inside that blue thing there's a cluster of several thousand stars, including several stars which are hundreds of thousands of times brighter than the sun. You can't even see it in the visible. Completely hidden. Well, not completely. With a really sensitive telescope, you can say, yeah, they're in there.
Idea City, the smartest people, the biggest ideas.
So back to the immensity and the romance of astronomy and cosmology. When I got interested in it, it seemed that there was a reigning theory and it was reasonably easy to understand. There was a Big Bang, there was a rapid inflation, huge expansion that was going to reach some limit of elasticity and eventually come snapping back. So the history of the universe was some sequence of expansions and contractions. And if we were around when it came shooting back, well, tough luck. And then it was discovered that, no, that's not the way it works. The universe is expanding constantly, in fact, at an ever-accelerating rate. And indeed, there may be more than one universe. In fact, as Marcel pointed out, as many as 10 in the current theory, parallel membranes, dimensions, whatever. So to grapple with this ever-changing portrait of what it is that actually happened, I've asked Barth Netterfield to come back. Barth is from the U of T, a great astronomer. He's a Canadian astronomer, which means that he's underfunded and that he has to be very, very resourceful. Barth is proposing the use of high-altitude balloon-borne scopes that can do a lot of what the space-based scopes can do, but at a fraction of the cost. Well done, Barth.
Hi. Up till now, about half the starlight of the universe has been hidden, not visible. And I'm going to talk to you today about an experiment we just finished up where we've been able to reveal this missing starlight of the universe. And also in the process, on a more personal note, I'm going to talk a bit about how during this big adventure, God reminded me that he's in control and not me. So it's been great already this morning. We've been able to see some people talking about the immensity of the universe. Because whenever you're doing astrophysics, you've got to keep reminding yourself just how big it is. Now, I could tell you, well, the sun's 150 million miles away, but we don't have any way of putting into our heads what is 150 million miles. So let's go to a scale model of the universe, maybe 1 in 10 billion. So we're going to shrink everything by a factor of 10 billion, which we can't fathom anyway. But OK, fine. In this scale model of the universe, the sun, which is the nearest star to us, the sun is going to be 15 centimeters across. OK? The sun, in this scale model universe, 1 in 10 billion, the Earth is only 1.2 millimeters across. It's like one of those cake decorations. And it's 15 meters away. We got our solar system. You saw in the power of 10, sort of roughly how big that works. Maybe Neptune is about, half a kilometer from here. The nearest star, besides the sun to us, is another sphere, about 15 centimeters across. It is on the Alaska-Yukon border. And the sun, and the nearest star, Alpha Centauri, and the 100 billion closest stars form a cloud of stars called the Milky Way. And here we have it here. And I hope you've all had a chance to get outside the city and look at the Milky Way. Because if you haven't, you need to, because it's so cool. Now, if you've been out there, you'll probably notice this glowing band of stars. And that glowing band, that's not like fog. It's actually stars. 100 billion stars. Spaced like one here, one on the Alaska-Yukon border, and 100 billion more. So, OK, sorry. My 1 in 10 billion scale model universe, it hasn't been scaled enough. We still can't picture it. Well, that's all right. Another thing you'll notice, in this picture of the Milky Way, this is actually a picture of the whole sky, They're these black bands, dark bands, but you can't see through them. This is actually dust. Well, what do I mean by dust? I mean dust, like soot. It's the expulsion from old stars that have died. It's blocking our view of what's going on inside. And what's going on inside is very interesting. It's where new stars are forming. And it's where the brightest stars live, and we can't see them. Here's the nearest galaxy to ours, Andromeda. You see the same thing. You can see those black bands interspersed with the clouds. Inside of those black bands are the brightest stars. It's where stars are forming. We want to see it. How are we going to do this? It turns out anything that's warm glows. Something that's a few thousand degrees of, like, say, a light bulb filament or the sun, it glows with visible light. Your eyes can see it. As you go colder, instead of glowing with visible light, the object will start glowing with infrared light. So imagine maybe there's a log in the fireplace, it's kind of glowing red. Most of the light coming off of that thing is coming off in infrared. Color of light your eyes can't see, but your hand can feel it. You get close, you can feel the radiation hitting your hand. It's real light, you just can't see it. Or you get even colder, like say, well, a few hundred degrees above absolute zero, like say you, or the dog in the picture in the bottom left. It's glowing with infrared light exclusively. You turn off the lights, you can't see me. But I'm glowing with infrared light. If infrared camera, you can see me. Or if you can see the dog, and his eyes glowing because they're warmer. OK, so you get infrared camera. But it turns out that this dust we'd like to study, within which stars are forming, within which the brightest stars in the universe live, is hundreds of degrees below room temperature. It's a few tens of degrees above absolute zero. It's glowing with what's called submillimeter light. If we're going to see into this dust, understand star formation, see these missing stars, we need a submillimeter telescope. You can build one. The group I worked with at Caltech had built these detectors, beautifully sensitive, no problem. They can see submillimeter radiation, but you can't use it to look at the sky because it turns out the atmosphere is opaque to submillimeter radiation. Now, clearly, you can see through the air with visible light, like I can see you, hooray, okay. Submillimeter light, no such luck. So this is kind of a picture here across the horizontal axis is different colors of light, and it sort of tells you, trying to picture what kinds of radiation can go through the atmosphere. Visible light shown by the rainbow can, radio waves down there. You can build radio telescopes and look at the sky. But right in here, where we want to observe these star-forming regions, submillimeter light doesn't penetrate the atmosphere. Can't do it. So up till now, there's been, well, essentially nothing done trying to look at this dust.
When we come back.
The NASA guy said, OK, this is a good place to land it. So we're bringing it down. We said, make it happen. So here we have blast on the parachute coming down, and this is the end of a really, really awesome flight.
Get the latest Idealist news, presenter information, and watch streaming video at www.ideacityonline.com.
Idea City, the smartest people, the biggest ideas.
A satellite's going to be launched. Actually, a satellite was launched about a month ago called the Herschel Space Telescope, designed to go and study this dust. In fact, we worked with the instrument team on it, and they provided our camera for our telescope. This is a $1 billion mission, which is expensive. And I'm a professor. I like having things I can build in the lab, having graduate students build it. You know, they're not going to get to build that. So this is what we do instead. We fly telescopes on giant balloons. Imagine a sandwich bag about 100 meters across. That's what these balloons are. Well, it's that kind of plastic, you know. Seriously. It can carry a 3-ton telescope, 35 kilometers high, and keep it up for weeks, assuming that you keep constant sunlight on it. If it gets dark, the gas cools and it kind of sinks. So if you can get rid of sunsets and sunrises for a few weeks, you can keep it up for a long time. Getting rid of sunsets is obvious. What do? Go to the Antarctic or the Arctic. Great. OK, so here's what we built. We built the BLAST telescope. It's a collaboration between us here in Canada at U of T and UBC, the US, and the UK. Started building it. I guess I was working on it when I talked to you 10 years ago. And it took a long time to build. It was a lot cheaper than Herschel. It was about 1% the cost. The whole mission, including all the flights, was about $7 million. Most of the work was done by our students, which is great. That's what makes the professor happy. So the balloon is only inflated 0.5% full. So you go outside and you launch it, and it starts out almost empty. And as it goes up, the gas expands till it gets to 35 kilometers, and then it pops. No. It's got a vent on the bottom of the balloon, which lets out the helium, and it comes to what's called float altitude. And then it can sit up there, 35 kilometers, as long as the sun doesn't go up or down, stay up there for weeks. So here you have the launch. The driver of the launch vehicle gets the telescope right underneath the balloon, and then lets go, because if it's not right underneath the balloon, it swings and hits the ground, and then the launch vehicle driver has some grumpy scientists to contend with. Okay, there, away it goes. I mean, grumpy is kind of the wrong word, right? When you spend 10 years of your life on this thing, it's pretty freaky. But, you know, you work hard. Okay, this thing's put together, it's working, away it goes. The next 2 weeks are spent doing this. So the telescope's hundreds or thousands of miles away pretty quickly. It gets blown across the other side of Antarctica. And the only way we can communicate with it is through a satellite link. We have a couple kilobits of bandwidth. Think about dial-up, except a lot slower. That's sort of our communication with the payload. So we obviously can't get all our images back. We can get just a small fraction. Enough to know that the thing's working, enough to know that we're getting really, really good data. So this makes us feel, what's the word? Happy. Flew around Antarctica after about 2 weeks on schedule. The cryogens ran out. Those liquid helium used to keep the detectors very, very cold so they can be sensitive enough to see what we're looking for. So the NASA guy said, okay, this is a good place to land it. So we're bringing it down. We said, make it happen. So here you have blast on the parachute coming down, and this is the end of a really, really awesome flight. All we got to do is get to the telescope, recover the tube. It's about this long, this big around, painted white. It's got the hard disks on it with all of our data. So, I mean, you know, what could possibly go wrong? So it turns out that, I'm sure you know this, people like to go to Antarctica for like adventures. And on the far side of Antarctica during this time, there was a group of adventurers who thought it would be a cool idea to parasail across Antarctica. People do cool things down there. They have their Iridium phone and their laptops and they're blogging saying, what's with Antarctica? There's no wind. Of course, on the opposite side of the continent, we didn't have that problem. Okay, that's a 120-foot parachute dragging a 2-ton telescope across the ice. Now, what was supposed to happen was the parachute was supposed to be released. But when the parachute opened, it was very violent. It destroyed the electronics that does that. Okay. As a Christian, I say to myself, God's in control. He does things for a reason. And I'm having a hard time understanding the reason for this. So the plane circled for about an hour, came back and said, yeah, about your telescope. They went out the next day with a twin otter and came back after about 8 hours and said, well, we found what's left of it. It's in a crevasse. I'll show you what a crevasse is in a second. But, you know, some pieces may have fallen off. If you want to borrow this, I wish I had time to wax eloquent about this. This is a DC-3 or C-47 built in 1942 during the war. I drove by it every day and said, I want to fly in that. I said, you can use the DC-3 and a crew and go look for it. Right, a tube this big around, painted white. 135-mile-long dragline. Yeah, okay, we're praying a lot. Okay, This is a cool picture. I wish I had my laser pointer because I can make dancing lines. On the bottom edge here is McMurdo Station, and we landed up on the plateau. You can see this range of mountains. Basically what happens is it's been snowing in Antarctica for hundreds of thousands of years and not melting. And so it just keeps getting deeper. These are, imagine the Rocky Mountains. Those are 7,000 and 8,000 foot mountains here, and the snow is filled up right to the top. And then it flows back down through these mountains down to the sea. And right at the top, where it starts to curve over, you get these crevasses. They're about 15 feet across, maybe half a kilometer or so deep, and then snow is bridged over the top so that you can, well, you can't really see them. You can from the air pretty easily. And about 2 miles, here, you can see the dragline over on the left-hand side. You can see up on top the crevasse field, and one of those little curves there, it just fell off. Nice place, you could land, no problem.
When we come back,
All those little blobs there are future stars. It's a cloud of gas and dust, which is in the process of collapsing down to become a star.
get the latest Idea City news instantly. Follow us on Twitter.
Idea City, the smartest people, the biggest ideas.
This is the Milky Way galaxy. You can see the dust clouds. That's the region that we looked at with BLAST, one of the regions. And you can see that there's, zooming in, you can see the stars, but you can also maybe see some sort of dark shadows. That's the dust we're trying to look at. And so the next picture is what we saw with BLAST in the same region, right on top of it. So here's invisible, and here's a completely new picture of the universe. This is seeing the hidden Milky Way. What are we looking at? Things that are blue are places where there's ongoing star formation, massive levels of star formation. This cloud here that I'm pointing to on the left, inside that blue thing there's a cluster of several thousand stars, including several stars which are hundreds of thousands of times brighter than the sun. You can't even see it in the visible. Completely hidden. Well, not completely. With a really sensitive telescope, you can say, yeah, they're in there. But here, there they are. The red things, those are things that are cold. Star formation is going to happen there, but it hasn't quite yet. We can zoom into that sort of axe head, and you can see what's going on. This is a cloud of gas. It's around 2,200 light years from here. So if you like metric, it's 21 exameters. An exameter is a billion meters. Okay. And all those little blobs there are future stars. It's a cloud of gas and dust, which is in the process of collapsing down to become a star. Now we can return to our scale universe. We can try to picture the sizes here again. Remember we said the sun was a grapefruit, and the nearest star is in the Alaska Yukon border. These clouds are something like the size from here to Montreal. They're huge. And they're going to collapse to form a star about this big. So they're really wispy. I mean, space is really empty, even when it's full. But here we're seeing star formation at the very earliest stages. This is pretty cool. Now, there's another ongoing problem, which is that there's a lot of stars in the universe. Where'd they form? When did they form? We also spent a bunch of time looking at a blank field outside of our galaxy. And what we see here, look on the top right here, is that mottled look. What is that? That is thousands of obscured galaxies within which star formation is happening at hundreds or even thousands of times the rate of our galaxy. We're looking back now 8 billion years into the past to when the majority of the stars in our universe formed. And half of the starlight of the universe is hidden in these enshrouded galaxies. So, and since that time, star formation rate of the universe has plummeted and it's now a fraction of what it was at this time. So this is what we've been doing the last few years. Thanks. It's always fun to talk to people who are interested in what you're talking about. It's a riot. It's really fun. I want to get back to the next speaker.